Hey you guys, it's Professor Vet. Welcome to Chapter 6 on Oddities of Nature and the World of Numbers. Okay, there's a lot of material here in this chapter, so I'm going to try to go through this outline. I'll periodically refer to it and let you know where we are. We're going to start here first with Oddities of Nature. Okay, this looks like some type of bleeding iceberg. Or at the very least, this does look like blood. You know, it looks like maybe a seal or something was there if you've ever seen a polar bear attack or something. But it turns out this is actually just rust in the water. There's iron oxide there and creates this effect. It looks like a bleeding rock. Very striking, but if you saw it, you weren't familiar with it, you might not be able to properly identify it. Here we have, believe it or not, this is a volcano which has blue lava, and it has to do with the nature of the gases released by the lava that makes it blue. This is, bizarrely enough, and apparently this does seem to be real, although I'm a little bit dubious still. There's apparently a lake which is so rich in sort of deposits, mineral deposits, that anything that gets in there becomes calcified, dies and becomes calcified. I'm a little dubious, but it's certainly quite possible. And at the very least, this would be striking evidence for you if you were to see it. It's an oddity of nature. This here is a lenticular cloud. Now, this doesn't quite look like a UFO, but it's getting there. And in fact, there are lots of famous cases of unidentified flying objects that turn out to be just extraordinarily rare natural phenomena. Here we have a really interesting phenomenon. I hope you can see it in this picture. This rock appears to be moving across the desert floor in Death Valley. Now this happens in a few places, and the best thinking is that somehow ice crystals form between the stone and the bed of the earth, or right behind the rock, and these ice crystals slowly over time expand just a teensy bit and they move the rock. But these rocks do appear to move across the desert floor. Kind of an oddity of nature, to be sure. This is one of my total favorites. I was absolutely sure this had to be something man-made, but it turns out this is a pufferfish. This was made off the coast of Japan by a male pufferfish. Apparently they do a certain type of dance, and when they do it, or some type of movement, I believe it does have to do with the mating ritual, it generates this pattern in the sand. If you're not familiar with pufferfish, you haven't seen that before, you might mistake that for some type of an imprint, perhaps made by an artifact. Now, what does all this stuff have to do with anything? It really boils down to this. Nature is really weird. And our intuitions about nature are not necessarily a guide to truth. So if you're running across something and it's anomalous, make sure you understand, well, gosh, this could just be an oddity of nature, right? So if you're talking about light in the sky behaving strangely, perhaps it's something that you just don't have much experience with, and that should be a call not necessarily to deny what you've seen, but certainly to investigate natural phenomena further. Okay, next up, probability estimates and bias. If I had to boil this section down, I'd say we're not so good at determining probabilities. Let me give you an example. One thing that we do commonly is the availability error. And what happens is we tend to remember evidence that sticks out. And when we do, our mind has a little shortcut and says, well, if we can think of it, then it must be important or influential. So one way that this happens is that we misjudge probabilities has to do with the availability error. And the idea is that someone remembers evidence that sticks out. So an example of this might be, suppose I go and I do a lot of research on the type of car I want to buy, and I decide, okay, I'm going to buy, a Volt 5000 or something. And then I'm just about to go to the dealership, and one of my buddies calls and he says, "What are you doing?" And I tell him, and I said, "I'm going to go buy a Volt." And he says, "Oh gosh, John had that car and he hated it." Now, and I say, "Well, gosh, then I'm just going to go with what John says. If he hated it, and I probably will too." But if I've done my research properly and I've looked at hundreds of people who've conducted, customer satisfaction surveys, and I've looked at the data involved pertaining to the maintenance of the car and its safety and so forth, those kinds of that kind of information anyway is a lot better than just one isolated story. And so the problem with availability here is that if you can think of it, it must be influential. And this is it's not that you're not thinking about it. This is simply something your brain will do. Your brain will fire this way. And so you have to be wary of it, because it's essentially a way for you to lose track of hits and misses with regard to certain theories. It's a way to sort of cherry pick. So, there are lots of examples of this, but essentially there are cases where people do cold readings, and the book goes on about this in some great detail, where you can give a reading to someone and you'd say, "Oh, I'm thinking of a Jay or Jane. Who's Jane? Or is there a name that starts with J?" And then someone says, "Oh, yeah, there is a J. It's Jerome, and it's my uncle." Later on, when you ask somebody, "Well, how accurate was the psychic?" They'll tell you, "Oh, they got my uncle's name right." Well, they might have given you a number of different guesses there, right? They might have said a name that starts with J, or a Jerome or a John. And because we remember the hits, right? It's kind of like confirmation bias. Because we can bring those hits to mind, we tend to think that someone might be more accurate than they otherwise are. A good case of this is Maureen Flynn. There's a famous, you can Google her, Maureen Flynn, and there's a case of her doing a cold reading, and they analyze a transcript of it, and they find availability error there. People will often say something like, "Well, gosh, I hear so many paranormal stories. There's got to be something to it somewhere." In fact, I love Howard Hughes. He has a great podcast, and he just committed this availability error. He said, "Gosh, when I think of the number of stories that get told on this show, there's just got to be something there." Well, not necessarily. Just because you can remember these things doesn't mean that they're representative of samples at large. Okay. Believability is similar to ease of recall. What happens is, and why is there an availability error? It's because these stories are very vivid to us, and they come to mind, and so we tend to pick them up better. Another example I think I like a lot is the strawberry allergy. If I ask you how many people, how common is a strawberry allergy, you'd immediately try to think of people that who have a strawberry allergy. I know I did, and I thought of one person that I think I knew in 4th grade or something like that to my knowledge had a strawberry allergy. But the incidence of strawberry allergies across the population is not it's not represented well by how easily I can remember someone who has a strawberry allergy, right? I may have just been exposed to a bad run of people who have it, or I may have never encountered somebody who had the allergy, I may have encountered somebody who had the allergy but didn't tell me about it, right? So there are problems with trying to generalize from what you can remember. And so you need to rely on data that's systematic, and that's really the availability error. You just remember something because you remember something, you think it's more prevalent or more influential. Remember, this is an important point. What am I going to be tested on, right? Look for examples of someone remembering something or hearing something and it sticks. In those cases, those are availability errors, and that will certainly be a cue for you during the exam. Okay, another problem we have when it comes to estimating probabilities is our apparently innate tendency to be optimistic. So you see yourself as more likely than your peers to have something good happen to you, and you're less likely to have something bad happen to you. So you say, I won't get sick, right? Well, I won't get sick next month. I usually don't get sick. Well, you probably get sick about the average, what everybody gets sick, but we have a tendency to see ourselves as somehow more privileged, healthier than we are, smarter than we are, that sort of thing, and it just appears to be part of our evolutionary wiring. Or just us as people, or just part of our nature, I guess you could say. That would be a less controversial way for some people to hear it. As a result, we can become misguided as when we have to determine the probability of something happening to us. Okay, third problem, or third item in our checklist regarding the oddities of nature and the law of large numbers. Math ignorance. This really boils down to, it's well presented as the birthday problem. Basically, we're bad at math, and specifically, we're really bad at large numbers and probabilities for large numbers. Your brain just doesn't quite do it properly. It needs to, when your brain tries to think about these things sort of automatically, it fails to do them properly, and I'll show you an example, just be better. Okay, what is the minimum number of people you need in a group for it to be more likely than not that two of them have the same birthday? Okay, so think about this for a second. 365 days in the year. How many people would you need to get in a room to make it more likely than not that two of them share the same birthday? So, one way to think about this is that there are 365 days in a year. If you divide that number in half, you get, 180 something, right? 183, I think, or 182. So you might think, gosh, well, in order to make it more likely than not, a better than 50% chance that I have a birthday, you may think I'm going to need to have like 160 some odd people in the room. Right, because every day, you have 365 days. If half of them are taken, then it's more likely than not two people in the room have the same birthday. It turns out that's totally wrong. The number is much smaller. You only need to have 23 people in a room in order to make it more likely than not that two people share a birthday. How does this work? By the way, this is just a little cake here. This is a cake rack. Someone obviously didn't read the instructions, but okay, just a little brevity. How does this work? Well, there's a way to calculate what the chances are that someone has a unique birthday is, right? So if we wanted to determine the likelihood that someone in the room shares a birthday with someone, or they have a unique birthday, we would do this. We take a calculation of the uniqueness, and we would then multiply it by itself. We get a 100% chance of a unique birthday if there's one person in the room, and there's a 0% chance that there's a match. But if I want to determine the likelihood that two people in the room share a birthday, I'm going to multiply the first number by the likelihood that they share a birthday, which is the second number. So how does all this work? It's not a math class, but what essentially happens is as you add more and more and more people, the probability grows, but it doesn't grow in a steady stream like you think. It grows exponentially very, very quickly, so that when you get to 23 people right here, you can see that probability increases very quickly that two people are going to share a birthday. What that means is that there are going to be really, really remarkable coincidences that happen between people. And it's not because it's necessarily meant to be. It's just that we don't understand large numbers very well. We don't understand exponents very well. we had let's think about this a different way. You might meet somebody and gosh, you've got the same middle name, or you're the same height or the same weight, and this seems to be miraculous that there's this interesting combination. But when you think about the number of traits that you have, and you spread those out long enough, your first name, your last name, your middle name, the height, the weight, the age, whether or not you have siblings, the clothing you like to wear, what you do, where you were born, what your nationality is, the languages that you speak, the things that you eat, the friends you have, the hobbies you have, where you live, and so forth. You've got a lot of things that you can share in common with somebody. And you're not going to necessarily be really good at determining when these things are going to be probable. So to boil the birthday problem down for purposes of the exam, you need to know that the birthday problem shows us that people underestimate how probable some apparently unlikely events are. So that kind of leads very, very naturally into a discussion of coincidences. This is hilarious, by the way. Obviously, a bunny and a kitty looking very much alike, but it's not because they share any genes, right? It's just that it happens to be that way. So there are lots of coincidences when people look at, for example, the connections between Lincoln and Kennedy, and they're both born in these times, and they both were assassinated, and so forth. These are these strange coincidences that exist between Lincoln and Kennedy. A student of Freud's, Carl Jung, claims that this is synchronicity. He has a special term for it. But what do all these coincidences mean? You can see them in different presidents. Our book's author does a good job of that. You can see this with 9/11. There are all sorts of sort of attempts at numerology and so forth. What does all this mean? Well, it doesn't mean much. You're going to have coincidences, and they're going to take place, and they're going to be very, very strange, and they will seem bizarre to you. And I'll get to that a little bit more with the law of very large numbers below. We need to cover randomness first. So coincidences are related to math ignorance for us, remember, because we're not good at judging probabilities naturally. Let's jump on to randomness. Most of the time when we think of randomness, we think of, sort of this uniformly random event. If I'm flipping heads and tails in a series of coins, randomly, you would be surprised to see that I got, 3 heads in a row, then a tails, then 2 heads, then 2 tails, then a heads, then a tails. And if this was a random flip, you might expect it to go something like heads, tails, heads, tails, heads, tails. But it turns out that's not what randomness is. Even random sequences have clumps of what look like uniformity to them. So here you can see this looks kind of clumpy. We have tails 3 times in a row, and we have heads 3 times in a row. But these are in fact random sequences. It just doesn't look random to us. And you hear this a lot with regard to something called the phenomena of the hot hand. If you talk to something like a basketball player, they'll talk about a good shooting night where they had a string, and they made several baskets in a row, and they just had a hot hand that night. It turns out that's a fallacy. There is no such thing as a hot hand. Each shot is an individual event. It's just that in any sequence of randomness, you are going to get strings of events that result in the same event. So if you have people shooting basketballs like Kobe Bryant, you're going to have some remarkable sequences where he makes 10 shots in a row. Doesn't mean he has a hot hand. It means that when you expand the data and you look at the number of shots that Kobe has taken, he always returns to his average. And so if I'm flipping coins, I may get 3 or 4 heads in a row, and it may look strange, but as the data set increases, that string of randomness will be evened out, and it'll return to normal. Okay. Again, I tried to put the font in red here to help you guys out because I know this is a long lecture. Okay, let's look at the law of very large numbers. And actually, we're following the book's outline here, but truthfully, 3, 4, and 6 could go together quite nicely. The law of very large numbers. Okay, you guys, let's talk about death premonitions and the law of very large numbers. Death premonition, if you've had it, can be quite startling. Essentially, you think of somebody, and then it turns out later that they pass right around that time. How likely is this going to be that something like this would occur? When it does happen to you, it can really be unsettling, and you think, gosh, what's the connection there? Well, it turns out, just statistically, there's a really good chance that this is going to happen anyway, without any established psychic connection. So the book runs through this in really good fashion. So we're just going to briefly overview it here. Okay, so let's just review how this works. Suppose you have 5 minutes of thought per person, and there are these 105,102 5-minute intervals in a year. So, supposing we have a list of 10 people who died in the last year, the chances that any of those 10 people are the ones being thought of, any of those 10 people who died are the person who's being thought of at the time, that's 1 out of 105,102, so that's, 1 out of 100,000 roughly. So for 10 doomed people, 10 people who are going to die in that year, your chances are 10 out of 100,000. So what does this all mean? It means you've kind of got a 1 out of 10,000 chance of thinking of a person who's going to die in the next year, within that 5-minute interval that they actually die in. But there are 300 million people, so maybe the odds for me are 1 in 10,000. But if you have 300 million people to choose from, then you're going to have 25,000 people in the U.S. For the year who have death premonitions come true just by chance, because you have 300 million people. That's over 70 a day just by chance. So you're going to have some strange and remarkable events happen like that, where you're thinking of someone and they die, or you're thinking of someone and they call. And that's just because you have to remember you're dealing with extremely large numbers, and we are not good at calculating probabilities for extremely large numbers. Another way to think about this is the lottery fallacy. The book doesn't go into this, but it should. This is Solomon Jackson Jr. winning the Powerball. Wow, look at that. $259 million. What are the odds of Solomon winning the lottery? I mean, it's got to be hundreds of millions to 1 to be sure. But that's the wrong question to ask. The question is not what are the odds of Solomon winning the lottery. The question is what are the odds of someone winning the lottery, right? In just the same way that when we look at death premonitions, we say, okay, chances are for me I've got a 1 out of 10,000 chance of thinking of a person within 5 minutes that they die. And then I think of this person and then they die. What are the odds? 1 in 10,000. Must be some connection there. No, not when you see that there are 300 million people in the USA, right? So again, this is just to make the statistical point that you're dealing with such a large number. This is going to happen. So if it does happen to you, it shouldn't be surprising. It happens to somebody. So it's the same thing with the lottery. What are the chances of you winning the lottery? Not super good. What are the chances of someone winning the lottery? It's almost a statistical certainty that someone will eventually win the lottery because you have such large numbers. Okay? All right. Moving on, you can see this could take place with prophetic dreams. You have a dream that there's a fire or something like that, and then there's a fire. So you can run this. You take the number of dreams a night, then the number of dreams you have per week. You forget most of those unless you encounter something that makes you recall the dream, and the dream seems prophetic. And then here Dr. Smith just runs the numbers for us, right? 1 dream per day, 300 million people. So that's 109 billion dreams per year. Some are going to be remembered for sure. Okay. He runs the same thing here with Littlewood's Law of Miracles. There is certainly a more involved discussion regarding the nature of miracles that we can have in a philosophy of religion course. This is just strictly construed as a statistical, how do I put it? It's kind of a statistical law. It's a statistical point. You don't need to consider the metaphysics, but in a philosophy of religion course we would, and there's a lot of really interesting stuff you can do when you talk about miracles. But the takeaway is essentially that we underestimate the probability of unusual events. So, 1 in a million, you're going to calculate the chances of something happen. You're going to have a 1 in a million event happen to you every month. Okay. Everyone gets a miracle a month. Nothing spooky. Okay, so now we're just going to talk briefly about science and how science deals with chance. This is an important point, at least just for general understanding. Scientists are aware of the availability error. They're aware of our inability to understand large numbers and in particular exponential growth. And so science has a method in place that helps us avoid some of these biases. So for instance, a positive result reported in a journal, because we're aware that journals have a publication bias, we would want to make sure that those results are replicated prior to being accepted by the scientific community. Also, when we're testing a group of people, we need to make sure that we have a big enough sample and that the individuals involved in the sample are sufficiently varied. They have to be varied with regard to what you're testing, but also you have to have a group that does not receive a control factor. So these are the control groups, right? So they're not receiving a medication or something like that in order to test whether or not what you're doing has any correlation at all. I won't talk too much about arbitrary stop points, but they are somewhat interesting. Basically, the idea is this. If I'm testing, say, for a certain psychic phenomena, and I have a string of 16 misses, as an investigator, I may be inclined to say, well, let's stop now and pick up again a little bit later when you get hot. But those types of arbitrary stop points are effectively a way of kind of cherry-picking data. Once you're not getting the hits that you like, then you stop testing, and that will over time affect your results. You'll get more positive results because you're refusing to test when you're not getting those results. Don't worry about it if it doesn't make a ton of sense, but it is just a general point. Okay, now the book makes a lot of psychic bias, and the general idea here is people who tend to understand chance events and tend to have a better understanding of probability realize that you could have a death premonition and it could simply be the result of chance because you're dealing with such large numbers. Now, as an individual, when you have that experience, it's incredibly unsettling, but and it can be very difficult to not have that impact your belief. But as we know, there are a certain number of death premonitions or miracles and what have you that will occur just by chance alone. And so again, here you're remembering a 300 million population size in just the U.S. alone. So a chance baseline shift or psychic bias is just when someone underestimates the probability of an event. So a good example might be, and they think instead that it has to be some sort of psychic event or something like that. I had once in my life, someone was thinking of somebody and the phone rang and they picked it up and it was that person. And they said, my gosh, what are the odds? Well, it seems pretty amazing when you consider one person and one thought. But when you take over your entire life, the number of people you think about, and the fact that those people, at least to some degree, are going to call you because they probably have your phone number. At some point in your life, you're going to be thinking about somebody and they will call. It's just based on the law of statistics, right? You're just going to have very large numbers. You're eventually going to get a hit. Doesn't necessarily mean that there's anything else to it. Okay, and again, just an important point. I'm not going to quiz you ever on whether or not you believe in psychics. It's just not relevant. But just understand that this is a skeptical line of argumentation that attempts to explain these connections without recourse to supernatural powers. You may not agree with them, and that's perfectly fine. You're not tested on that. You just have to know what the car is. You do not need to drive the car or take it home, but you have to know, well, you have to test drive the car. You don't have to buy it. Okay? All right. That concludes the lecture. If you guys have any questions or concerns, email me, rvitt@lbcc.edu, and good luck on the exam.